previous lecture we were discussing about the weighted residual method and its basic understanding. So, let us take up from there. Let us say that you have a governing differential equation with a linear operator on y, Ly equal to 0. So, if you now substitute y approximate, then L of y approximate will not be equal to 0, and we call this equal to some residual which is non-zero. Our objective is to have a method which tries to minimize this residual. So, what is done in the weighted residual method is this residual is multiplied by a weighting function and it is integrated over the entire domain. So, here if it is a one dimensional problem, the domain is x where y is a function of x, integrated over the domain and this is set to 0. So, the error is minimized in a weighted integral or weighted residual sense. Now, the big question remains that what should we take as the approximating function. So, the approximating function is a trial, it is a guess. So, you are trying with a function and trying to make sure that the function is appropriate in a way that it minimizes the error in a weighted integral sense. Now, let us see how we can achieve that. We will look into an example and try to follow that example to see that how that is achievable, but before that we learn certain terminologies and concepts which we borrow onto the examples. So, first terminology is the trial function. The trial function is nothing but the y approximate and in this trial function the y approximate can be chosen in many ways. We will see later on that polynomial is one of the convenient methods or one of the convenient choices of the function, but it need not always be a polynomial function, it can be any function provided it satisfies certain characteristics. What are those conditions? So, the trial function should satisfy the essential boundary condition, should be continuous again we should keep in mind that it should satisfy the essential boundary condition is one of the very key requirements. Essential boundary condition is basically what is the value of the variable for a second order problem as an example. So, for higher order problems it can also be the derivative, whatever it is we have seen earlier through the variational formulation that what do we mean by essential boundary condition, and that essential boundary condition should be such that it should be, or rather the choice of the trial function should be such that it satisfies the essential boundary condition. It should be continuous, and once we say it should be continuous over the domain of the definition of the function, and derivatives of trial function must be square integrable. So, derivative square integrable means, for example, if you have y dy approximate dx whole square, integral of that one must be less than infinity. So, it should be a bounded integral. Square integral means integral of square of the derivative, basically you are doing. So, this type of requirement is a very important and stringent requirement. It shows a boundedness of the function. So that its integral is not unbounded. Why this type of thing is necessary? Because if you have say an operator a y y, bilinear operator, then often the bilinear operator can take the form of the square, and if it is integrated, its integral should be less than infinity, so that such functions are bounded. That is very important. Now, you can also have higher order derivatives. We have to see that what is the highest order derivative necessary. If you have a variational formulation for a second order differential problem, you may at most require a first order derivative continuity, because you have already reduced the order of continuity by integration by parts. So that your derivative requirement, highest order derivative requirement for satisfaction of the continuity is the first order derivative for a second order problem. Similarly, for a fourth order problem, it would be a second order highest order derivative continuity requirement. So, if it is a second order problem, then you only require up to the dy dx type of term for your continuity requirement. You do not require any higher order derivative for corresponding to your variational formulation. However, you will require that if you do not go through the variational formulation. So, you may also have the weighted residual method implemented without going through the variational formulation, because variational formulation gives us a clue that you have to multiply this with a weighting function. The weighting function is having a same meaning as that of a variation or a similar meaning as that of a variation, but it does not mean that you have to go through the roots of variational formulation. We will see that you can have any arbitrary choice of the weighting function, of course consistent with certain constraints, but the whole understanding is that for a second order problem also, if you do not go through the variational formulation, you will require a second order derivative continuity if you do not reduce the continuity requirement through integration by parts. So, the variational formulation is sometimes weak formulation, because you reduce the or you weaken the requirement of the order of the continuity of the approximating function. But if you do not require, if you do not employ that as a strategy and simply do the integration without doing integration by parts, then obviously you require the continuity up to the highest order derivative. So, it is not the first order derivative for a second order problem, it is then a second order derivative for a second order problem. This we must keep in mind. So, depends on through which route we are going. Are we going through integration by parts route, or we are straight away integrating without integrating by parts. Now, this type of function, so here the first order derivative is square integrable, we call it as H1 function in functional space. So, there could be several types of functions like H1 function, H2 function, like that. So, H1 function in a functional space is such that its first derivative is square integrable. If it is H2 function, then its second derivative has to be square integrable, like that. So, this superscript stands for the order of the derivative which is square integrable. Now, this is the trial function requirement. Now, what about the requirements of the weighting function? That is W. It should satisfy homogeneous part of the essential boundary condition. What is homogeneous part of the essential boundary condition? So, let us say that you are having a boundary value problem with y at one of the boundary is equal to 5. So, the weighting function should satisfy its corresponding homogeneous part. So, the weighting function should satisfy the requirement that it is equal to what? It is equal to 0. Homogeneous means this right hand side is 0. So, why it is so? See, if y is specified, then variation in y is 0 and the weighting function has the similar meaning as that of variation in y, and therefore, the weighting function is 0 at the points where the function itself is defined. So, that is why wherever you have the essential boundary condition, that means that function is defined, the corresponding variation which is reflected through the weighting function is 0. So, that should be satisfied by the weighting function, that requirement should be satisfied by the weighting function. Weighting function also should be continuous. You see, when we are designing the trial function and the weighting function, we are bothering ourselves so much about the essential boundary condition, not the natural boundary condition, because the natural boundary condition is automatically incorporated through the formalisms of the variational method. So, you do not have to forcefully incorporate the natural boundary condition, that is why it is called as natural boundary condition. So, you do not have to forcefully incorporate it. Now, this is a brief background. Now, with this background, let us try to understand that how differently you can choose the trial function and the weighting function based on some particular methods. So, some specific examples. Let us say we are interested to solve a heat transfer problem, one dimensional steady state heat transfer with uniform thermal conductivity and heat source S. So, if that is the case, we have seen earlier that the governing equation becomes this equal to 0. This is the governing differential equation. So, that d2t dx2 plus s by k equal to 0. To be able to solve this problem numerically, let us assume some value of s by k in consistent units. Let us say this is 100. What should be the unit of this? Say this is, what is the unit of d2t dx2? Kelvin per meter square. So, this is like 100 Kelvin per meter square, say. We are not putting the unit here, but it is with consistent units. And let us say that the boundary conditions are such that at x equal to 0 you have t equal to 0, and at x equal to 10 t equal to 0. So, our problem becomes the problem of solving a differential equation, a very simple differential equation of this form: d square y dx by dx square plus 100 equal to 0, and at x equal to 0 y equal to 0, at x equal to 10 y equal to 0. So, this is the problem that we intend to solve. So, when we intend to solve it, there are various ways in which you can approximate. Remember, we intend to solve it approximately. The objective of this demonstration is not to show that how to solve it exactly, because that is very simple and straightforward. So, let us not bother about that, let us bother about the approximate solution. So, for an approximate solution we need what? If you have to go through the method of weighted residual, you need a trial function and you need a weighting function. So, there are different methods, accordingly you can have different trial and weighting functions. So, let us take one example. The first example will be the least square method. So, in the least square method what we will do? We will try to minimize the error in a least square sense. So, what we will be doing? First of all, in place of y we have some y approximate, that is there in all methods. So, there is a trial function. Now, you substitute the trial function in the governing equation. So, you have this plus 100, this is equal to the residual R. So, what you are interested in? You are interested to minimize, the value of this square of R. So, how do you do it? You find out what is R square, integrate it over the domain and try to minimize that. So, when you say that you are interested to minimize R square, you mean integrate to minimize the sum of R square. So, what you are trying to do? At each and every x there is a corresponding error, R is the error. You are finding square of the error at each and every x and summing it up. If it were discrete points, it would have been a sigma or summation, but because it is a continuous function, you have an integration. So, you are having, so this is, so physically what is the meaning of this? Physically you are finding the sum of the squares of residuals at each and every point. Why square? Because if you just find out the residual itself and find the sum of it, then it can be misleading, because some of the residuals may be positive, some of the residuals may be negative, the total sum may be 0, giving a false illusion that as if the error is 0 or error is very small, but actually that may be because of nullification of some positive error with some negative error. Alternatively, one could actually do with the mod of the residual, but because the algebra with the mod is tedious, one does not go through the mod, but one basically finds the square, which anyway is always positive and therefore is indicative of the magnitude of the error, and then try to minimize that. So, this now needs to be minimized. Now, when it is to be minimized, there must be some unknown parameter through which it needs to be minimized. So, now let us come to the choice of the approximating function. It can be many. Now, one of the choices could be that you choose a polynomial. So, if you choose a polynomial, remember it is not a must, it is just an example. Say we consider it to be a second order polynomial with one parameter. So, what can be its form? So, what are the requirements that it should satisfy? It should be continuous. Obviously, we will, when we consider polynomial, by nature it is continuous. So, we do not have to bother about the continuity of it, but most importantly it should satisfy the essential boundary conditions. That means, it should be a polynomial of such type that at x equal to 0 it should be 0 and at x equal to 10 it should be 0, and it is a second order polynomial by our choice. Remember, you could also choose higher order or lower order polynomials, and general expectation is that higher order polynomials will give you less error because you have considered more number of terms. And with one parameter means there will be one unknown parameter which you are interested to find out. So, a general form of the polynomial can be x into 10 minus x, because this is a second order one. You have constructed it by deliberately choosing it product of two first order functions, so that it is a second order function. Now, it satisfies the essential boundary condition, and you consider a parameter a, which is a single parameter, which is a multiplying parameter. You want to find out this a such that this is minimized, so that this is minimized. So, this is your y approximate. So, once you have this y approximate, next is what is your r then. So, let us just open it up. So, 10 ax minus ax square dy approximate dx the second order derivative minus 2a. So, what will be the value of r? So, r becomes minus 2a plus 100. Now, you have to minimize this one, r square dx integral of that. That means you have only one parameter here, a, so if this needs to be minimized, then its derivative with respect to a is 0, because a is the only unknown parameter. So, that means you can write, you can take this derivative inside the integral, because the limits are functions of x which are not dependent on a. So, you can take this inside the integral and you can write this as 2r So, you can see that although it is a least square method by name, it is not a weighted residual method by name, but by implication it is a special case of the weighted residual method, where the weighting function is nothing but del r del a. Okay. So, let us find out the weighting function. Weighting function is minus 2. So, integral of minus 2a plus 100 to minus 2 dx, the limit of x equal to 0 to 10, that is equal to 0. That is the outcome of our formulation least square method, which we have seen may be perceived as a special case of the weighted residual method. So, from here what is the value of a? So, minus 2a plus 100 will be equal to 0, that is the coefficient, because the integrand itself is not 0. So, that means a is equal to 50. Thank you.